All right, buckle up, everybody, because we're diving headfirst into the wild world of quantum gravity. It's kind of crazy, right? We have these two awesome theories: quantum mechanics, for the tiny stuff, and then general relativity for all the big stuff, like gravity. And they work so well on their own.
They really do.
But when you try to put them together, it's like, well, chaos, like trying to mix oil and water.
Yeah, they just don't get along. And it gets especially tricky when we start thinking about those really extreme parts of the universe.
Right.
Like what in the world is going on at the edge of a black hole?
Wow.
Or even wilder, what was the universe like right at the very beginning?
Yeah. Like, did time even exist before the Big Bang?
I guess my head spin just thinking about it. I gotta admit, going through all your sources, I definitely got lost a few times in all those theoretical equations.
It can be a lot, definitely.
So today, let's try to keep it, like, down to earth. And hopefully we can figure out what clues we might actually have to test these wild ideas.
Sounds good. And just to be clear, it's not like quantum mechanics or general relativity are wrong. Right.
They both work amazingly well in their own domains. The real issue is this: scale. It seems like these quantum gravity effects, they only show up at this super tiny level
Oh, yeah, I remember reading about that.
called the Planck scale.
The Planck scale.
And
Wow.
we're talking tiny, like 10 to the power of next 35 meters.
That's like unimaginably small.
Yeah, it's way beyond anything we can see with even our best technology.
Okay, so teeny tiny scale, huge theoretical problem. So from your expert point of view, what are like the best approaches to actually solving this quantum gravity mystery?
Well, there are a few leading contenders, each with its own, pluses and
Of
minuses.
course.
One that a lot of people find really elegant is string theory.
String theory.
And the core idea there is pretty radical. So instead of thinking about the universe being made of these tiny points, these particles, what if everything was actually a tiny vibrating string?
Okay, so instead of electrons and quarks, it's just these little strings wiggling around.
You got it.
I mean, it sounds pretty cool.
It's an elegant idea.
But I remember reading about like extra dimensions being involved, and that
Yeah.
always seemed a little too sci-fi for me.
I get that. It definitely requires you to stretch your imagination a bit.
A bit.
So string theory, to make the math work out, it needs more spatial dimensions than the 3 that we experience every day.
Right, right.
So often that means 10 or even 11 dimensions. But don't worry, the idea is that these extra dimensions are what we call compactified. They're curled up so small that we can't directly see them.
So like they're tucked away down there at the Planck scale with all the other weird quantum stuff?
Exactly, they're hiding out.
Okay, maybe they are. But let's move on to another contender you mentioned, loop quantum gravity. What is that all about?
So loop quantum gravity takes a different approach. Instead of these, point particles, it focuses on quantizing space-time itself.
Whoa, okay.
So instead of space-time being this smooth, continuous fabric, imagine it's more like woven from these tiny interconnected loops, almost like chainmail.
Like chainmail, okay.
And what's interesting about loop quantum gravity is that it does all this without needing those extra dimensions.
Oh, so points for simplicity there.
Definitely. It's a more economical approach in a way.
But I mean, every theory has its hurdles to overcome.
Oh, absolutely.
So what are some of the challenges for loop quantum gravity?
Well, one of the biggest is figuring out how to go from that chainmail, loopy picture to the smooth space-time we experience every day.
Right, right. It's got to connect back to what we actually see.
Exactly. It's a really tough problem.
But, I mean, not a deal breaker.
No, not necessarily. Just a puzzle to solve.
Got it. So we've got strings, loops, and then there's this one. Even the name sounds complicated. Causal dynamical triangulation. Did I even say that right?
You got it.
Okay.
CDT, as it's often called, it's kind of like building space-time out of Legos. Imagine these tiny building blocks of space-time constantly evolving over time.
Okay, that actually makes sense.
Right.
So, like, if we zoomed in super, super close, the universe would look pixelated.
Yeah, exactly. But like with the other approaches, CDT has its own challenges.
I bet.
It's a newer idea.
Okay.
And the math is incredibly complex.
Right.
And connecting it to observations, that's really difficult.
Right, back to that pesky scale issue.
Exactly.
Now, there was one more contender in the mix that sounded a little less, well, intimidating. Asymptotic safety. Did I get that right?
Yeah, you got it. Asymptotic safety, it's kind of a dark horse in this race.
That dark horse. Okay.
It's more of a hope than a fully formed theory at this point.
Okay, I see.
The idea is, what if gravity itself just starts behaving nicely at extremely high energies,
Okay.
like the kind you might have seen just after the Big Bang.
So, like, maybe gravity isn't so messy if we just look at it in the right way.
Right. And if that's true, it could solve a lot of those really complex math problems we run into. And maybe, just maybe, we don't even need those extra dimensions or to come up with totally new physics. It's still very early days,
I see.
but it's definitely an intriguing possibility.
So, we've got a sense of the main players here. We've got strings, we've got loops, space-time Legos, and maybe gravity just being well behaved. But gotta ask, all this sounds incredibly abstract. What's the math actually like behind these theories? I think I'm ready to have my mind blown.
Well, get ready for some serious brain twisting because the math involved in quantum gravity, it's not easy.
All right, lay it on me. What are some of the key math tools that come into play here?
One of the big ones that you see in a lot of these different approaches is something called a path integral.
A path integral.
So imagine you're trying to figure out the probability of, say, a particle going from point A to point B.
Okay.
In classical physics, there's usually like one clear path it takes. But in quantum mechanics, things get a little weird.
I bet they do.
You have to consider all the possible paths that particle could take, even the ones that seem like totally crazy.
So it's like a quantum choose your own adventure, but every path is happening at the same time.
Pretty much. Now try to imagine doing that not just for one particle, but for like the entire shape of the universe. That's what we're trying to do with path integrals in quantum gravity. Sum up all the possible shapes and configurations of spacetime.
Whoa. That's a lot of paths to add up, and I'm guessing the math gets a little intense.
Yeah, it gets really intense really fast. And then you run into another problem called renormalization.
Renormalization, right?
So in quantum field theory, you often get these infinities popping up in your calculations.
Infinities. Uh-oh.
Yeah, not ideal. Renormalization is basically a way to kind of get rid of those infinities and make sense of the results. But with gravity, it's even trickier. Gravity is what we call non-renormalizable in the traditional sense of the usual tricks. They don't really work.
So it's like trying to balance your checkbook when you have infinite expenses. No wonder this is such a hard problem.
Exactly. And then you've got this whole world of non-commutative geometry. This is where things get really strange.
Okay, let's hear it.
At the tiniest levels, like down at the Planck scale, space itself, well, it might not behave like we expect.
Okay.
Imagine a world where coordinates are all messed up, where x times y doesn't equal y times x. It's mind-bending stuff. But some physicists think we might need this kind of weird geometry to really describe space-time at that quantum level.
Okay, I'm starting to understand why this quantum gravity puzzle has been stumping physicists for so long. But if the math is this hard and we can't even see these effects directly, how are we supposed to find evidence for any of these theories?
That's the million-dollar question. Direct experiments at the Planck scale, they're just not possible with the technology we have right now. But there are a few ways we might be able to see these quantum gravity effects indirectly.
Okay, so what kind of clues are we looking for?
Well, one potential place to look is in the cosmic microwave background radiation.
The CMB, right.
It's basically a baby picture of the universe, a snapshot of the radiation left over from the Big Bang.
Oh, wow.
And within those tiny, tiny temperature variations in the CMB, there might be these subtle signatures, fingerprints of quantum gravity effects from the very, very beginning of the universe.
So it's like we're trying to find these faint whispers from the Big Bang.
Yeah, exactly. It's a huge challenge, but the payoff would be incredible.
I bet.
And then you have gravitational waves. You know those ripples in space-time caused by black holes colliding?
Oh, yeah, gravitational waves have been all over the news lately. So how do those tie into quantum gravity?
Well, if our detectors get sensitive enough, we might be able to pick up tiny little deviations from what general relativity predicts for those waves.
Okay.
And those deviations, they could be signs of quantum gravity at work.
It's like we're trying to catch those gravitational waves gossiping about the quantum world. What about high-energy astrophysics? I know you mentioned black holes and cosmic rays earlier. Can they give us any clues?
Definitely. Black holes are kind of like natural laboratories for extreme gravity. And if we could observe something called Hawking radiation, well, that would be a huge step forward.
Hold on, Hawking radiation? I feel like I've heard of that. Can you give me a refresher?
Sure. It gets a little complex, but the basic idea is this. Quantum effects near the event horizon of a black hole, that point of no return, can actually create pairs of particles.
Okay.
One particle falls into the black hole, the other escapes as radiation.
I see.
And that radiation carries away a little bit of the black hole's mass and energy. And over a really, really long time, it could actually cause the black hole to completely evaporate.
Oh, so black holes aren't actually completely black.
Not necessarily.
There might be this faint glow of like quantum stuff around them.
That's the idea. And finding that Hawking radiation, it would be huge. It would really confirm that quantum effects are happening in these super strong gravity environments. And then you've got ultra high energy cosmic rays. These particles, they're zipping through space with way more energy than we can create in even our biggest particle accelerators.
So they're like little natural particle colliders just out there in the universe.
Exactly. And there's a chance those cosmic rays, they could be interacting with space-time in ways that, reveal quantum gravity effects.
Okay, so we've got all these potential clues hidden in the cosmic microwave background and gravitational waves in how black holes behave and in these super energetic particles. It sounds like we're getting closer to actually being able to test these mind-blowing ideas.
Yeah.
But I gotta ask, why should the average person even care about this stuff? I mean, it's super cool, but does it really affect our lives?
That's a great question. And I get it. Quantum gravity, it seems pretty abstract, but it has some pretty profound implications. This isn't just about equations on a chalkboard. We're talking about trying to answer some of the biggest mysteries humans have ever wondered about. Like, how did the universe begin? What happens at the edge of a black hole? Are there other universes out there?
So you're saying that understanding quantum gravity could actually help us answer these huge questions?
Absolutely. Like, take the Big Bang. Our current theories, they kind of break down when we try to go all the way back to the very beginning. But quantum gravity, it might be the missing piece of the puzzle.
Okay.
It could help us understand what truly happened in those first moments of the universe.
Wow. So we might be able to look behind the curtain of the Big Bang.
That's the hope.
That's amazing. What about black holes? You mentioned earlier that they're like natural laboratories for gravity.
Right. Black holes, they're these extreme objects that really push our understanding of physics to the limit. Remember that black hole information paradox we talked about before?
Yeah, the whole thing about information being lost in a black hole, which breaks quantum mechanics. My head's still spinning from that one.
It's a tricky one. But quantum gravity could be the key to solving that paradox.
Okay.
It might give us a new way of understanding how information behaves in those really intense gravity situations.
So maybe information isn't actually destroyed after all. Maybe it's just encoded in a way we don't understand yet, like on the surface of the black hole or something.
Some theories definitely suggest that possibility.
That's wild.
And even beyond that, quantum gravity, it might finally help us unify all the forces of nature.
Oh, right. There's gravity, electromagnetism, the weak force, the strong force.
Exactly. And physicists have been trying to unify them for forever.
I know. It's like the holy grail of physics.
It really is. The dream is to have this theory of everything.
The theory of everything.
One framework that describes all these forces as different aspects of one ultimate force. And quantum gravity, well, it might be the key to finally making that happen.
So we're talking about rewriting the textbooks here, revolutionizing our understanding of the universe, maybe even discovering technologies we can't even imagine right now.
That's the incredible potential of quantum gravity.
Right. You've definitely convinced me. Quantum gravity is definitely worth caring about.
So where do we go from here? What's next for quantum gravity?
Yeah, that's the big question. What does the future hold?
Well, I think the future of this field is honestly incredibly exciting.
I mean, it has to be, right?
Yeah. It might take us, generations to fully figure it all out.
Yeah.
But we're making progress.
That's what matters.
We've got new technologies coming online, new math tools being developed, and a whole community of brilliant people working on this.
That's awesome.
It really feels like we're on the verge of some big breakthroughs.
Okay, so give me a glimpse into the future. What are you, as an expert, most excited about in the world of quantum gravity?
Well, one area that I think has huge potential is gravitational wave astronomy.
Gravitational waves, yeah.
We've already seen some incredible discoveries from LIGO and Virgo, detecting those ripples in space-time from black holes and neutron stars colliding.
Yeah, it's been amazing to see.
It really has. But imagine detectors that are even more sensitive, like the planned LISA mission.
ELISA, okay, tell me about that.
So LISA stands for Laser Interferometer Space Antenna.
Catchy.
It's going to be this space-based gravitational wave observatory.
Wait.
3 spacecraft, millions of kilometers apart.
Wow.
With that kind of setup, we'll be able to detect gravitational waves from all over the universe.
Yeah.
and with incredible precision.
So, like, we'll be able to listen to the universe with, like, a much bigger ear.
Exactly.
That's so cool.
And who knows, maybe hidden within those signals, we'll find those tiny whispers of quantum gravity. Imagine being able to detect the echoes of the Big Bang, or maybe even hints of other universes.
Okay, now that would be mind-blowing.
Right.
But what about experiments here on Earth?
Yeah.
Any chance we can test these ideas in a lab?
Well, directly probing the Planck scale, that's still way beyond what we can do.
Okay.
But, that doesn't mean we can't learn anything.
Mm.
There are some super clever experiments being designed to look at how quantum mechanics and gravity interact in new ways.
Oh, okay, like what?
For example, some researchers are trying to create superpositions of, like, macroscopic objects,
Yeah.
tiny mirrors, maybe even small living organisms.
Hold on, you're saying we might be able to actually see quantum effects, like superposition, at a scale that we can actually, like, observe?
That's the hope. And if they can pull it off, it could really blur the lines between that weird quantum world and, our everyday experience.
Wow.
And who knows, it might even reveal connections between gravity and quantum stuff that we haven't even thought of yet.
That would be huge.
It really would. You also mentioned new mathematical tools earlier.
Right. Right.
There's a lot happening on the theoretical side, too.
Cool.
We're seeing these tools from other areas of physics, like holographic duality and quantum information theory, being used to study quantum gravity in really interesting ways.
Okay.
So holographic duality, in a really simplified way, it suggests this deep connection between gravity in a certain space-time and a quantum theory that exists on its boundary.
Okay.
It's kind of like saying the universe is a hologram, where information about the 3D interior is, like, encoded on this 2D surface.
Okay. I need a minute to process that one.
It's definitely
Uh-huh.
mind-bending. But the point is, these new approaches, they're giving us whole new ways of thinking about quantum gravity and its connections to other parts of physics.
It sounds like it's becoming this, like, really interdisciplinary
Oh,
field,
absolutely.
bringing in all sorts of ideas.
Pulling in insights from cosmology, particle physics, condensed matter physics, even computer science.
It feels like this quest for quantum gravity, it's really pushing the limits of what we can do as humans.
It is. And that's part of what makes it so inspiring. It's not just about equations. It's about that human desire to explore, to understand the universe and where we fit into it all.
That's beautifully said.
Thank you.
So as we wrap up our deep dive here, what's the one thing you hope people listening will take away from all this?
I think it's this. The universe is far stranger and more wonderful than we can even begin to imagine. And trying to understand it, even if it takes us centuries, that's one of the most important things we humans can do.
Absolutely. And to everyone listening out there, keep those questions coming, keep exploring, and never stop being curious about the universe. We'll see you next time.